All right, welcome. Hey, today on the Paigecast, we're going to talk about Newton's second law of motion. Now, here are the outcomes of this chapter. All of these 5 things you need to be able to define: acceleration, weight, mass, terminal speed, air drag, free fall, and friction. You can see that the second law of motion, the equation for acceleration, the relationship between acceleration and velocity, and then that relationship between acceleration, mass, acceleration, force, and acceleration and friction. And we'll talk about all of those. Now, Galileo developed the concept of acceleration. And basically, you can see right here that acceleration is the change in velocity divided by the time interval. Now, we know from last chapter that the change in velocity, we're talking about a change in velocity, okay, we're either going to speed up, slow down, or change our direction. And so that's what we're talking about, that change divided by the time interval, how long it takes to do that. All right, and as you can see down here, acceleration can be 3 things: speed up, slow down, or change direction. Okay, now when we talk about force versus acceleration, when we apply a force, it will cause an acceleration. And you can see the second one here, it depends on the net force. All right, and the net force and the acceleration are directly proportional, which means that as I increase the net force, I increase the acceleration. So you can see this example, if I double the force, what happens to the acceleration? Well, if I double the force, I double the acceleration. Now, mass and inertia. Okay, remember in our first Newton's first law, we talked about inertia. Okay, well, mass is the amount of matter an object has. All right, so and we can see that the more mass, the more inertia. Okay, now I want to make sure that we get this last one down here. Mass is not weight. Okay. Weight is the force of gravity. Now, if I'm on Earth and I weigh 200 pounds, I have a mass. But if I go to the moon, I still have a mass, but my weight is going to be less because of the different gravity. Right. Now, when we look at this, we're talking about mass, okay, you can be weightless, but you still have mass. If I'm out in space, which would be cool, I could be weightless, all right? And mass is related to gravity. The more mass, the higher the gravity, the more weight you have. Now, right here, we're going to talk about 1 kilogram equals 9.8 newtons. For the sake of argument, we're just going to round that to 10. So we're going to say that 1 kilogram mass has a weight of about 10 newtons. All right? And you can see that that corresponds to the acceleration of gravity. And again, we're just going to round that to 10. Okay? Now we're going to talk about mass versus acceleration. Okay? Now, remember this, that if the mass is greater, then we have a greater inertia. So the more massive objects are more difficult to accelerate. As we watched yesterday in the demonstration when Canfield came up and pushed on me and Holcomb, all right? More massive, I didn't move as much as Holcomb did, okay? So we say that mass and acceleration are inversely proportional, which means that if I increase the mass, my acceleration decreases, and vice versa, okay? So that takes it to Newton's second law. And to put it, technically, the acceleration produced by a net force of an object is directly proportional to the net force, is in the same direction as the net force, and inversely proportional to the mass of the object. In other words, what we're saying is that if I have the more force, the more acceleration. The more mass, the less the acceleration. And here is a formula that we can use, and you can see here on the left right here, the sum of the forces equals the mass times the acceleration. And notice that little arrow up there, that's a vector. And here, that little arrow there, we have a vector. So the only forces that act on the object, okay? If I push a car and that car starts to accelerate, then I've applied a net force to it, all right? And so we can see that acceleration is directly proportional to force, which means the more force, the more acceleration. Inversely proportional to mass. So the more mass, the less acceleration, okay? Friction. We'll talk about friction. Friction resists motion. And basically, friction is when one object rubs against another. And that can happen in all 3 states. As I walk through the air, I'm experiencing air friction. I'm experiencing friction with the air molecules. If I swim in a pool, all right, I'm experiencing resistance there, friction in that. So friction is always in a direction opposite of the motion of direction. All right, and right there, just a little graphic there, we can see that if motion is going this way, that I have friction in the reverse way. Now notice that both of these arrows are the same length because those vectors are the same if we are in a state of constant velocity. Right? Now, friction depends on a couple things. Number one, the kind of material. okay? I can tell, the tabletop is very smooth, so there's not much friction there, okay? A gravel road, there'd be much more friction on that gravel road because it's rougher than the blacktop, okay? Now, how much are they pressed together, okay? If I press down on the table really hard and push, I can create more friction, all right? And then what's the incline? Am I going uphill or downhill, okay? That's very important. Okay? Now, remember Galileo, when he said then he rolled down the hill, then as it rolled down the hill, it gained speed, and then as it rolled up the hill, it started to slow down speed, okay? Now, remember this, acceleration does not depend on mass. Galileo could not say why acceleration was equal in different mass objects, okay? He couldn't understand that, all right? Newton's law does, though, okay? Right here, we know that weight is a measure of gravitational force. So the net force of an object should be equal to the force of an object that is in free fall. So in other words, right here, we know that acceleration equals force divided by mass. Well, our force is our weight divided by our mass. Well, as my weight increases, so does my mass. So we can see that that is the same. All right. Now, we talk about acceleration versus air drag. And air drag is kind of resistance in the air. Two things it depends on. How fast you're going and the surface area. You're driving down the highway and I put my hand up like this, okay, and I can see that as the air hits it, okay, there's a lot of surface area there, okay. Now, if I put my hand this way, notice there's not much surface area there, so I have less resistance, okay. All right, skydiving, I've jumped out of a plane before. Maybe we'll watch that video, but anyway, as I'm falling through the air, when my chute opens up, I have much more surface area, so therefore it slows me down, all right. Now, what happens to the net force if the air drag builds up to equal weight? I'm not accelerating anymore. Okay, I'm still falling, but I'm not gaining speed, and we call that terminal velocity. Okay, so when acceleration terminates, the diver has reached terminal speed. Okay, I'm not going to fall any faster, and then if we take in the direction that I'm falling, well, now we're talking terminal velocity. All right, and so heavier objects will have greater acceleration, which means they'll reach terminal speed faster. Okay, if I were to jump out of a plane and a smaller person were to jump out of a plane, I would reach terminal speed faster. We'll both reach terminal speed, but I'll get there faster. And which, for a typical human, it's about 150 to 200 kilometers per hour, about 120 miles an hour. Now, right there, that kind of ends our Newton's second law.